We will now look at another application of free field theory, which is to compute the interaction energy between two sources. First, recall what we did for a particle. We started with a field which was in its vacuum, and then we applied a time-dependent source at some given position of space, which excited the field and then created a disturbance of the field which propagates in space-time. And the relationship between the time frequency and the space frequency of this disturbance has to be on mass shell for the disturbance to propagate efficiently. We will now look at a different situation where we have a source acting at some position in space, independent in time, and then deforming the field from its original vacuum configuration. The deformation of the field induced by the static source costs some energy E of j. If I want to get this energy, I will need a Hamiltonian. And so far, the only time we saw a Hamiltonian was when we expressed the evolution operator to get the amplitude from vacuum to vacuum over an infinite time, where the energy will be the expectation value of the Hamiltonian on the vacuum. We don't know what it is yet because we don't know what the Hamiltonian is. However, we already solved this amplitude using path integral for a free field theory. If I choose the reference of energy so that the energy of the vacuum is 0, I see that Z of 0 without source will simply equal to 1. Note that it's important for our source to be static, that is, to not depend on time, because otherwise the Hamiltonian will be time dependent, and in this case the evolution operator will take a more complicated form. In fact, what we would like is not the energy induced by one source, but the interaction energy between two sources. When the two sources are far apart, the total energy is just the independent sum of E of j1 and E of j2. But when the two sources get closer to each other, the disturbance induced by one of the sources will be felt by the other source. There is clearly a region where both sources act together to push on the field. As a result, there is an additional interaction energy between the two sources, and that's this energy I'm interested to calculate. Because we are in a free field theory, we managed to find an expression for W. Because the source is the sum of two sources J1 and J2, we see that W will have four terms. One with the product of J1 with J1, one with J1 and J2, J2 and J1, J2 and J2. W11 and W22 will be associated to the energy change in the field when only one source is applying to this field. And that's not what I'm interested in. What I'm interested in is the interaction energy, so the part of the energy which is here only because I have two sources, so that will be associated to W12 and W21. And of course, by symmetry, these two terms are the same. Now I am ready to apply this relationship between the energy and the effective action W. So far, the only thing I have imposed on my sources is that they are static and they act only on some defined region of space. So let's define this region of space by simply a delta function. I could add a constant in front of the delta function, but that will not change the final results. So one source is pushing in x1 and the other one is pushing in x2. Our sources are only acting in space and not in time, therefore it is convenient to separate these four integrals into a space and time components. Because we use delta function in space for our sources, that will kill our space integrals. So that gets rid of already 6 integrals. We now try to solve the time integral. So we have 2 of them, 1 over x naught and 1 over y naught. So we will start with the one on y naught. Y naught. We see that y naught only appears in the exponential term here. Therefore, we have an integral over y naught of exponential I k naught y naught. And that I know is proportional to a delta function. So this delta function is killing my integral over k naught, and it forces k naught to be 0, so in the exponent, and also in the denominator. We now look at the other time integral over x naught, but because k naught is equal to 0, that kills the only dependency of the integrand into x naught. So this does not look good, because this is an integral which goes from minus infinity to plus infinity. However, remember that this is a time integral, and we already have an infinite time on the left-hand side, and this is the same one in fact. Therefore, being physicists, we don't mind about cancelling 2 infinites on each side of the equation. If you are bothered about that, just remember that what we call an infinite time as physicists is in fact a long time with respect to the typical time scale of the system we are studying. Here our sources are static, and remember that I want to start from vacuum to vacuum. So I could imagine that I start from vacuum and have a time-dependent source, but which is only plugged in very slowly with an adiabatic process, and therefore that will turn my infinite time into a long but finite time, and therefore the cancellation on the left and right hand side will be perfectly justified. Remember also that our epsilon has been introduced in order for the integral to be well defined. However, our final physical result should not depend on epsilon. Notice that since k naught has been killed, we have minus k squared minus m squared. So as long as m is not equal to 0, we never have a division by 0. So we can now get rid of the I epsilon safely. So we started with 12 integrals, and we now have only 3 left. So we did a pretty good job into reducing the complexity of our problem. Unfortunately, the remaining 3 integrals require a little bit more work. So we will leave that for later, and I will give you the solution. This is a potential energy between 2 sources mediated by a scalar field, which is called the Yukawa potential. It depends on the distance r between the sources, and it is attractive because it's negative and diverges for small distance. Its typical range is given by the inverse of the mass. Remember that we are in natural units. Recall that the mass here is defined as a constant appearing in the quadratic term of the potential energy for the field. But it is also the mass of the particles we obtain by creating disturbance of the field which propagates on mass shell. The static sources we are using here also create disturbances of the field. However, these disturbances do not propagate on mass shell. So in the language of real and virtual particles, they will be creating virtual particles. So in other words, the sources interact by exchanging virtual particles. More correctly, they are interacting via disturbances of a scalar field which are out of mass shell. Interestingly, this is the same field which is responsible for particles which propagate on mass shell, and also for the interaction between the sources. Usually these sources come from other fields and other particles. So if we take, for instance, the example of nucleons, imagine the 2 sources are 2 nucleons sitting at some position in space. And if they interact with a scalar field, then if they are close enough, they will have an attraction between each other mediated by this scalar field. So if you see an interaction between particles, like the interaction between nucleons, you can deduce that a field exists which mediates this interaction. If the field exists, then you can deduce that there should be a particle associated to on mass shell excitations of this field. So that was the reasoning of Yukawa, who was trying to explain the strong interaction between nucleons responsible for the existence of the nuclei. Because the nuclei are so small, the interaction between the nucleons is short range, and it's typically 1 to 2 femtometers. So that defines the range of the interaction. And therefore, because the range is the opposite of the mass, that also give an estimate of the masses which will come from excitations of this field propagating on mass shell, and the predicted masses were of the order of 100 to 200 mega electron volt, or MeV. And that was indeed discovered a few years after Yukawa's prediction, and that was a pion which was found with a mass of around 140-150 MeV per c squared. Finally, look at what happens if you take m equal to 0. Then the numerator is just 1, so we recover 1 over r potential energy. So that means that whenever we have a potential energy in 1 over r, the mediator of the corresponding interaction has to be massless. This is how we know that the photon is massless, because the Coulomb energy is in 1 over r. And also, this is how we know that the graviton, if it exists, must be massless as well, because the gravitational interaction is in 1 over r.